Hi, welcome to P6.3, Patterns and Expressions with Variables. So we've talked a little bit about patterns already in P6.1 and 2. So we've actually talked about variables as well, and variables are just numbers that are represented with maybe a letter of the alphabet, like X. So there I just defined a variable for you. They are going to use, in this unit, they use variables and patterns and expressions for problems, and a couple of the problems are with perimeter and area. And you'll remember that perimeter is the distance around the outside of an object, like a fence. And area is the actual amount of space that something takes up, like an area rug. Okay, so for perimeter, you're adding all sides to get the length of your fence. But for area, you have to multiply length times width. Okay, little review there. Describing and representing geometric patterns, and that might be relevant to First Nations artwork. Using variables to show commutative property. Now this is just a fancy word that means it doesn't matter what order you put it in. Okay, so if I'm going to add 5 plus 7, it's exactly the same as 7 plus 5. It doesn't matter what order it is, and that works for adding and multiplying. That's what commutative property is. Okay. Writing expressions for a pattern in a table, writing expressions or equations that describe a pattern rule. So here's those two words we talked about before, expressions and equations. Remember that equations have equal signs. Expressions do not. They might just have something like 2r. So we know that 2r represents some sort of number, but we can't figure out what the r is because we don't have any equal signs. Equations, on the other hand, are something that you can figure out because they have the equal sign. Oh, and there you go. You can explain the difference between expressions and equations. You could probably do that already. And we're 2 minutes in. All right, your vocabulary, commutative. Again, that means it doesn't matter what order you put it in. 3 times 2 is exactly the same as 2 times 3. Okay, it works for adding and it works for multiplying. 4 plus 1 is the same as 1 plus 4. We can switch the order around, it doesn't matter. Variable, that's any letter. You can also use symbols too, if you want to see me draw more cats, because I'm pretty good at that. So we could say 2 cats yeah, he has no legs. Oh, let's give him legs. Okay, 2 cats equals 10. So think of the cats as maybe like a bag of cats, and we don't know how many are in the bag. But if I have 2 bags of cats, I'll end up with 10 cats. So what do you think's in the bag? Well, that cat symbol must represent the number 5, because 2 times 5 is what equals 10. So instead of using a letter, I used a nice symbol, my kitty cat there. Most of the time we use letters. We usually use X, Y, Z, A, B. Those are the common ones. We do not use O because it looks like 0. We do not use L because it looks like a 1. What else don't we use? You don't usually see capital letters as variables. We usually just use the small ones, lowercase. All right, formula, that's a recipe. So we're talking about the formula for area and perimeter just on the previous slide. So this is how we write a formula. Add all sides, okay? And so if we had a shape like this, that was 2 on this side and 4 on this side, we write perimeter equals 2 plus 4 plus 2 plus 4. One of the common misconceptions is that people will forget this side and just add the 2 and the 4. So remember to add all the sides. And You'll notice how I write my equation that the p's just keep dropping down in this column and the equal signs just keep dropping down, and I'm simplifying what I'm doing over here every time. So I got my formula and then I filled in the numbers, and now I'm going to actually solve it. 2 plus 4 is 6, and 6 and 6 is 12. So we're done. And maybe this was centimeters, I don't know. Let's put that up there. Okay, so that's how you use a formula. Area of a rectangle is length times width. And again, if we were going to find the area of that nice rectangle that I've drawn right there, you start with your formula, and then we're going to drop straight down every time. Fill in the numbers, and then solve. Area, we have to put the answer in centimeters squared because it's not just the distance around the edge of the fence, it's the distance that's inside that whole rectangle, and think of that as little squares all inside there. Okay. The difference between expression and equation. Which one has an equal sign? Well, the one that has the equa right there, equation. Okay, so expression, an example of an expression is 4b. What does the b stand for? Well, we don't know. We could guess, I suppose, but there's no actual way to know what number I was meaning when I wrote 4b. It might have been a 1. It might be 7001. Who knows? There's no way to solve it. If it has an equal sign, though, 4b equals 16. That means that 4 times something is 16. So what do you think the b stands for? 4 times something is 16. So let's figure it out like we did on the last unit. 4b equals 16. So we want to divide by 4 so that we can get our 4's out of there, Gandhi. And if we do that to one side, we must do it to the other side. So we divided by 4 on both sides. What's left of my little equation? Well, I have a b, so he can drop down and just be a b. I bring my equal signs straight down, and 16 divided by 4 is 4. We're done. So equations are the ones that you can actually solve. Expressions, they're just a way to represent a number, sort of temporary, I guess. All right, there's a question in your book or in the SCMAs, I can't remember where, and it talks about all the different ways that you could have a perimeter and an area of certain numbers. So let's start with the area of this here shape. We always start with our recipe, area equals length times width. And now we're going to fill in those numbers, 3 and the 5. Would it matter if I put 5 times 3? No, it would not, because multiplication and addition are commutative, and that means you can switch them around. And what is 3 times 5, my friends? I hope you said 15. Okay, and I'm just going to say units squared because it didn't say whether it was meters or centimeters or millimeters, so we're just going with units. 15 units squared. So if I was to count all these little squares, you would indeed find that there are 15 of them. Let's talk about the perimeter now. We start with our formula, and the instructions for perimeter say we have to add all sides. So let's put those numbers in. 3 plus 5. Sound good? Am I done? No, I'm not done, because what about the other two sides? Just because they're not labeled right there doesn't mean they don't exist, right? So if that side's 3, then the other side has to be 3, and this has to be 5. All right, drop down that p, drop down the equal sign. Let's add all our 3's and 5's together. 3 plus 5 is 8. So my perimeter is 16 units. So if I was to count all the way around the outside, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 units all the way around. Okay, so this is the length. That's what the perimeter means. So the example in your book says We're going to build a garden that has a perimeter of 30. We only have 30 meters of fence to work with. Okay? And so what are all the different shapes that you can make that will have a perimeter of 30? So let's work with this formula right here and think about it sort of backwards. What are all the ways that we can make a 30? And so maybe it was, maybe one side was 5. So that would mean the other side has to be 5. That's 10. There's 20 left. Okay, does that add up to 30? 5, 10, 20, 30. Yes. And so you could make a 5 by 10, say maybe a dog kennel or something. That's one way to get a perimeter of 30. And the area of that shape would be 5 times 10, which would be 50. Right? Okay, so let's do another way to do 30. Let's do, let's see, 3 plus 3, which is 6. That means we have to have 24, so this would have to be 12 and 12. Okay, so then we're a little bit shorter and a little bit longer. Okay, the area of that one, 3 times 12, is 36. So these are not the same area, are they? 50 is not the same as 36. But we have the same perimeter. It's still the same amount of fence. 3 plus 12 plus 3 plus 12 is equal to 5 plus 5 plus 10 plus 10, right? Because 30 is equal to 30. So it's interesting that you can have different areas with the same amount of fence, just depending on how you lay it out. Okay, let's try one more. Let's go 7 plus 7, that's 14. So that means that there's 16 left, so we'd have to go 8 plus 8. Does that equal 30? I think so. And so 7 and 8, it's very close to being square. Right? And when we figure out the area, 7 times 8, it has the largest area. So when you do this equation in your book or on the SCMA, this is the idea that they're trying to get you to understand, is that the more square your shape is, the larger the area is. Right? If we squish this out and had 1 plus 1, right, that makes 2, plus 14 plus 14, that's 28, 29, 30. So this also equals 30, right? But that would mean your shape is 1 and really, really long and skinny, right? 1 on this side and 14 on this side. And the area of that shape, 1 times 14, is 14. It's the smallest area. So the more square your shape is, the larger your area is. Okay, let's do a little patterning example. Complete the table below for a number of matches used in this geometric pattern. Okay, so this is figure 1, and there is one triangle. In figure 2, there are 2 triangles. In figure 3, right, this is figure 3, there are 3 triangles. So they've made a little chart with the number of triangles and the number of matches. So to make one triangle, you need 3 matches. To make 2, you need 6, 3, 9, etc., etc. So describe the pattern in words. Well, I would say that every time you add a triangle, you're adding 3 matches. So this one's pretty simple, right? So you can say maybe the triangle times 3, right? If the triangle is 5, the number of triangles is 5, you multiply that by 3 and that gives you your matches. So triangle times 3 gives you your matches. So I didn't describe it in words, I described it with symbols, but you could say for every triangle, use 3 matches. Okay, so that's a simple example. On this geometrical shape, we have a bit of a pattern happening. Let's call this figure 1, figure 2, and figure 3. Now in figure 1, you will notice there is 1 green triangle. In the next one we have 3, and in the last one we have 6. The white triangles, we start with 0, then we go to 1, and we go to 3. So you can find patterns between these numbers with what we've got already. We know that we're just adding 1 every time for the figure number, obviously, so the next one's going to be 4. Here you can see they've added 2 green ones, one right there, one right there. And then the next row they added 3. Okay, so obviously on the next row they're going to add 4. Okay. With the whites, they added 1, then they added 2, and I think we're going to add 3, and that'll be 6. You might also notice that these two numbers, when added together, equal the number of greens. So that's a bit of a pattern too. So let's fill in our pattern just mathematically without drawing all those crazy shapes. We know we're going to add 5, and that'll be 15. And then we're going to add 6, and that'll be 21. We're going to add 7. Right? And so on and so on. With the whites, we know, let's do it a different way. We know that those two, the figure number and the whites, when added together, gives you the greens. Okay, so let's figure out this one. This plus this equals 28. So this must be 21. And you might also see the pattern going this way, that this number ends up here, right? This number ends up here. So there's lots of different patterns going on. Okay, so this number obviously ends up here, and this number ends up here. So a pattern can have more than 2 parts. It can be more than just an XY input-output table or table of values. You could have 3 parts like we do here. Patterns can go horizontally, patterns can go vertically, patterns can go diagonally, as they did in this example. We could figure out the 10th pattern without figuring out the 8th and the 9th, because we can skip count if we wanted to. So patterns, mathematically, it makes more sense to do it with math than it does to draw out each and every triangle, especially if you draw like me. I don't know, this looks like pizza. That's a mushroom. Extra sauce. Okay, I'm hungry. Let's go eat.